Why microwave? Here. Yeah, very good. That's correct. Now we get purple to the C13. And as Nick said, we do that with the microwave, right? So now we're starting to think of the hardware that we need here. Good. Now, and then the last piece of the puzzle that makes this dissolution DNP is that I don't know if you've ever tried injecting something at 1.3 Kelvin into a patient, but I don't think it goes very well. I have tried it myself. So, in order to get this into a liquid state that we can inject, we have to dissolve it again very rapidly in a superheated buffer so that it comes out in a liquid form. And this has to be done very quickly. Once it's in a liquid form, we start losing that signal very rapidly based on the T1 that was in the previous lecture. So, good. So we've got the two main steps, and we've got more or less four general components to the system that we need to know about. First of all, yeah, everyone's good on that. Any questions? Good. Okay, so there are four main components to this polarizer. I'm a little hesitant handing this out, but I'm going to. There's so many capacities around. I've sort of put together a little, very dumbed down schematic of the polarizer that, probably end up, on Mom's fridge or something like that. My goal in handing this out is to at least give you a sense of what are the main components of this system that we need to be aware of. And so we labeled them, numbered them, included some different attachments in that. So, so hopefully everyone's got one. Did they make their way all around? I should have had 17 of them, so I don't know where the rest of them went. Okay, anyway. Great. Actually, I have an extra here, so I don't need an extra. Okay, so again, there are the four components. One of them we didn't mention with the electrons. If you cool down electrons, will you necessarily have polarization? Yes, no? There's another component that we need for polarization. It's very important. Yes, we need a magnetic field. Good. So, sorry, that's the last part. So, our magnetic field here is within here. So this is and it looks just like all the other magnets in this room, these big cans. This has a superconducting coil that is providing 3.35 Tesla of magnetic field. The other thing that it provides that's important for our system is a bath of liquid helium. So typically that's how you get the superconducting magnet. So the coil is submerged in liquid helium so that it can sustain a large enough current to produce that magnetic field. These systems are special in that they also utilize that helium in there also for the polarization in order to cool down our electrons. So that's the other part. So if you look at your diagram, that sort of middle stick that's in the middle of the superconducting magnet, that is what we call the variable temperature insert of VTI. So this is what contains the liquid helium. Essentially, it's cooled down, so that the sample sits in, and it's cooled to about 1.4 Kelvin. And so when the sample is inside, it'll be in one of these small cups, by the way. We'll see that in a second. It will be submerged in liquid helium, and at that temperature that's right here on in the software. Now, there are a few other things associated with the VTI. One is what's called the sample chamber. So there's actually where the cup sits in this thing, that chamber can actually move up and down. You can hear it moving if you listen to the processes that go on. So that moves actually up and down into a microwave cavity, and that's in the lower position, and then it moves up out of that microwave cavity, and in fact above the liquid helium level. That's important for loading and dissolution. There's a pump. That pump is a crucial part of cooling the system down from 4 Kelvin, which liquid helium is typically at, to 1.4 Kelvin. And then there are a few other valves that I can at least try to point out generally where they are. I'm not an expert in this, but there's an insert access valve that controls whether you can insert your sample or not. There is a needle valve that's for in here. here, what that does is that leaks the helium in from the big can here into the VTI. So that's how it fills with helium. When you see it filling with helium, it fills up. You can see it fill up on the screen. This ENP insert tells you how much helium is in that narrow part. By the way, this here, if you look, this is the start of the VTI, and then it just steps straight down. And yeah, feel free to move around so you can get a good look at it. Let's see what else. And then there's also an NMR coil in the system. So the NMR coil is around where that sample sits in superconducting magnets and in the VTI technically. And then all the computing stuff is here. So the NMR spectrometer computer and all that fun stuff is in here, synthesizers. And so we're doing solid-state NMR spectroscopy on C13 in order to measure the polarization of both sides. Great, so that's fun. One of the critical components we mentioned was the microwave source. That I see over here. So the microwave source, as we know, that's what induces the polarization transfer and it's the polarization to our carbon from the electron. The last part is the dissolution system. The nice thing is it's easy to identify. It's pretty much everything up here, more or less. So there are a few important components of the dissolution system. At the very top, where you see this sort of kind of dark green arrow-looking valve thing, that is what's called the bomb. Well, it's the entry to the bomb. That is what keeps keeps our dissolution buffer pressurized when we heat it to 170 to 180 degrees Celsius. Now, question: why do we need it to be pressurized? So let's say we're heating up water. We heat it up 70 degrees Celsius, 80, 90, 100 Celsius. What happens at that point? What's that? It boils. Yes, it turns into gas. So there's a way around that. If you keep it pressurized, it'll stay liquid. So that's why this thing goes up to a pressure of 10 bar G. So that's 10 bar above ambient pressure. So I believe ambient pressure is bar, right? So it's a little more than 10 times the pressure of ambient. So that's a good amount of pressure. Okay, there are a couple other valves that are important to note as well. You can see them actually here if you go into cleaning. There's what's called the chase gas valve. That basically opens so that the helium gas can come in. This helium gas tank is this closet here. And for this polarizer, there's one on the wall there. And then there's a solvent discharge valve. This valve basically lets stuff go through the dissolution system. Good. Now, it's very important that helium gas is the gas that is used basically in this whole system. Does anyone have any idea why we have to use helium gas? Why can't we use nitrogen, oxygen, freeze? Yes, that's right. So, and this will, I think, this may be a little more clear over time, but imagine that this thing is down and that you're chasing your liquid through, so it's coming down here, it's getting very close to the liquid helium, not quite, and then it's coming back up. If your gas gets down there and it's very close to liquid helium, which is colder than 4 Kelvin, or here it's 4 Kelvin. If it's the wrong type of gas, it's going to start liquefying and or freezing. So it is very, very important that helium gas is used essentially in all the components of this system. Even the pneumatics that control the sample chamber moving up and down are also helium. So that's an important thing relating to these, to the tanks and all that. Great. I want to first ask Jeremy if I said anything incorrectly about this system or anything you would add about it. Okay. My biggest fear is that I'm telling you something that's wrong. What's that? Okay, good. I'm thankful for that. Okay, then I'm going to ask, are there any questions so far about any of the individual components of the system? We're getting on time. It's almost which means I'm not going as fast as I thought. All right.
We can push things to later weeks too.
Sure.
Until I get the question.
Okay. All right. Well, at this point, so Mark VC used to do this. He was always very interactive and would let people basically, do this and that, and even, break the polarizer and stuff like that. I'm not Mark VC. I'm sort of still terrified of these systems even after a good number of years working with them. As I mentioned, they're quite fragile, so a lot of bad things can happen. So I'm basically going to go through more or less the basics of how to use these. So we start with the system. When we start with the system, typically, if no one's used it before, it'll be in one of two states. It'll typically be in what's known as the idle state. The idle state is where it's basically it's not using up helium. It's not, nothing's cooled down. This temperature will be, higher than the 1.4 Kelvin you need. It's mainly just, to preserve helium and, because it takes up certainly energy and it takes up valuable cryogens, particularly with the helium when it's in use. So idle is the state that these systems always need to be in, especially overnight and especially over weekends. When you're finished with the system and no one else is using it after you, you should put the system in idle. That's very important because that conserves the liquid helium that we're struggling to get it. It's not just us, but other people, U.S. and worldwide. Okay, but we're going to use this thing. So let's put it into cool down mode. You'll notice there's a nice button here that says cool down. Click that button. After that, we need to check this box that says fast liquid helium update. I think the main thing that this does is it actually boils off a little extra liquid helium in the BTI so as to increase the pressure. As Jeremy mentioned, these systems have a positive pressure basically in the BTI, and I think the main reason is to prevent air from getting in there. Yep. Yeah, so it's hard for things to flow into the system when things so that's good. There are important things about this. I mentioned that over time now, this liquid helium is going into this ENT insert. And that's controlled, as I said, via the needle valve. This is extra, but you can sort of see a couple of things. This is what's called the butterfly valve status. That tells how much the vacuum is being engaged, how it's reducing pressure in here. And then this indicator that's creeping up indicates how open the butterfly valve is. So this indicates that the system's leaking helium, liquid helium in, and then this is basically cooling down by applying vacuum. So these two things, again, you don't have to be an expert in all this, but just so you have at least a general sense of what's going on. In this process, it's basically just preparing the system so that the ENT insert has liquid helium in it, and that this temperature will be cold enough for you to polarize. As Jeremy mentioned, and as we've seen, our polarization depends very much upon the temperature. So more or less, you sort of wait until the system gets pretty close to a steady state. That's good. While we're waiting for that, we can demonstrate how to weigh a sample into a cup. So let's say we want to polarize the fire pit. I don't know if this is. I'm not going to put this over here. Sorry. We'll go to the 70 by clear, 700 by clear, which the salt means, or the salt part of the seed. The reason is if you try to solve this sample at the end, we're probably able to. The other thing along that is, remember, polarized greater than 50 by clear size here. You're going to want to increase the sample and make it nice. The issue with large volumes is that as you're loading, it's splash out your cup. It is eventually the light barrier. It will spill higher rate of dissolution. So those are very important. As a general rule, if you ever have a question about a system or you're not sure if it's a good or bad thing, don't be afraid to install. You don't have to be part of the staff. Work with your peers to make sure that you use the system appropriately itself. Very happy okay, great. All right. Now we've got that. Any questions? Just a lot of okay, so we're more or less cooled down at this point. As you can see the screen, this level typically gets to about 65. It's a little bit over, but and then this temperature is about 1.4. So we're pretty close to where we want to be when polarized. When we load samples, this is one of the trickier points, and it's important that users are trained well in this and that we practice a couple times on the polarizer before, more than a couple times before they can do this independently. This is the loading stick. This is what's used to get this cup inside the polarizer. If you look at your sheet, it's a sort of just a long tube. And so this is the bridge point between where we are now and where this cup needs to go. So, again, yeah, let's take some practice. The way it works is sort of two parts to this. You can see that there's some movement here. Basically, this part holds the cup, and then the outer metal sheet, when you pull back, it basically pushes the cup off. So what you can do is put your cup on like this, and it's kind of snugly there. And then if you pull the metal part and pull up on the black cap, the cup will become dislodged. So that's essentially what you do when you load a polarizer. So what we're going to do is we're going to load this sort of pouring empty cup into the polarizer for the sake of demonstration. So again, you put this on. When you put it on, your finger's on the top. Make sure that it's, you can also see that it should be all the way on. There's a sort of lip up the cup. It should be meshing with this. Now, in order to load, let's do this way off. So technically, this should be fully closed. You're always going to select normal sample here. Once we click next, it's go time. So things will start happening, and then importantly, the insert valve will open. The goal of loading well is, number one, not spilling. Number two, trying to do it quickly so that we minimize the time that the ambient air has to basically get sucked into the system. Ambient air is warm here. It wants to get colder, lower energy, so it naturally wants to basically get sucked into the system. That's combated by, as we said, the helium that is flowing out. Some of that, I think, also comes from the helium gas that is hooked up to, but it still gets in, and over time, that can cause the temperature to rise. That nitrogen, basically air, is sucked in. So, you're going to see this all happen very quickly. Again, this is something to practice, but we use like normal sample. Next, you're going to hear this start running. You're going to hear a couple things. You're going to hear first the sample chamber moving up. and then the valve opens. You open the doors. You have to go down all the way. If you need a ladder, that's great. Until you can't go down more, pull down the metal, pull up on the black part, out, and then close the door. Yep. And as quickly as you can, click that next button. You'll notice you hear the system moving again when you click the next button. That's the insert valve closing, and then the sample chamber goes down. So now if you did this wrong and things didn't work out, you can uncheck this. Because what this does is it basically tells the system what's inside. Is there a cup in there? Not a cup. It has no sensor of knowing, so this is how it knows. There are ways of telling the system, hey, there's a sample in there, or hey, there's not a sample in there. I'm not going to demonstrate that today. Okay, great. So we've loaded our fire base. Now, the next thing that we'll do is we want to set up our polarimeter. So the NMR spectrometer that's in here to measure our polarization buildup. That on this polarizer is controlled on this computer. And I don't know if you want to switch over here. I don't think I'll go through all the subtleties here. You're welcome to move that ladder backwards as well. But there's a program here called RINMR that we open. It up. I'm not going to go through too many aspects. Again, I think this would be more for basically, it'll ask you, what do you want to measure, and then all that. Basically, you set this up, and then when you're ready to, I'm going to first go over just polarizing. I don't know if we really have time to go over sweeps. I think that's something we can talk about at another time. We mentioned microwave frequency sweeps, which are important, especially for new formulations that you're testing, new compounds or old compounds and new solvents. It's good to do a sweep on those things. So, anyways, what we're going to see here, we're going to basically say that we're polarized pyruvate, right? So once you've set this up, there's a button here called Polarize Sample. On this, you'll set your frequency here. For some weird reason, you can't type anything in. You have to click the up and down arrows. Power. This power is always 25 milliwatts. It's a low power. Can anyone guess why a high power of microwave frequency could be bad for us? Heat up. Very good. Yes. So, yeah. So as we know, temperature is important. If the microwaves are too high of a power, they can start to heat up the sample. And if the sample heats up too much, it's not going to polarize. The nice thing about, as Jeremy mentioned, these sort of cost-effective polarizations, thermal mixing, they use fairly low powers of microwaves, so that's a great motive. 25 milliwatts is great. We don't need much else. You can decide whether you want to start polarizing right away or wait until the sample the system gets to a target temperature. It's usually, I think, about 0.2 Kelvin before or above the set point, which here I think is 1.35. We're going to do it right away. And then this box asks, do you want to measure your solid state polarization as you polarize? Do you want to use the NMR spectrometer in this? Usually the answer is yes. So if you click this, it'll also ask you how often do you want to measure your polarization. We used to set it to 300 seconds, usually not too much change. When I click the finish button, watch this screen here. You'll notice that you're gonna start seeing things happening on that computer. Good. And then what's gonna pop up? That's a graph. It's gonna show that nice exponential. Theoretically, with an empty cup, you should see nothing or just noise. As we know, as we alluded to, there's background to this thing. There's pyruvate spilled inside that BTI that the NMR coil is detecting, so you'll see that filter. Great. Well, not great. That's kind of a bummer. And you'll see here that the system generally tells you what's happening. So you're polarized. Excellent. That's a good thing. You know, you don't want to walk away, you know, for an hour and then come back and find out that you forgot to click that polarized sample button. That's very annoying, to say the least. So, by the way, when this insert is more or less full, you can uncheck this password with helium update. That's fine. So, okay, great. We're polarizing. Let me see. Okay. Again, this is a lot of stuff. Any questions up to this point? Questions?
Yeah. So this going system appears to be full of options. We are two mission close to is there a reason for that?
Oh, you need close and push the doors.
Just that model like that.
Yeah, it's the model. So this is designed with user safety in mind. So they decided that they wanted to be stored. That is a good point. On the other polarizer, it's the exact same machine, but minus the shell, which is why for many years it was nicknamed the Terminator. I mean, well, we call it the test bed, but if anyone ever calls it the Terminator, that's why. You know, it's like a movie, the robot. Exactly. So, yeah. Good. Okay, let's keep going. There's a couple other things here. So let's say it's been an hour. You know, time flies, and we're ready. You know, we've got. Let's say we're doing a mouse study. Our mouse is ready, waiting for an injection. So we're ready to do the dissolution. The first thing we need to do is remember we need some liquid, some buffer. Those typically live over here on this shelf. Yeah, you can put that here. So over here there are a bunch of these 5-1 syringes. Way out the buffer. Put it over here as well. We also put a burlap capture on that. And again, just like our prep, it's good practice to wait here, 0 scale, and then basically put it on here and get some weight if you want, more or less, you know, grams translate senses to moles. Mostly water, you know, 1 gram per mole. We have 4.3 grams, we've got more or less 1.2 moles. Or just so you get a sense of, you know, how to use this, how the pieces all fit together. Okay, we're ready to do our dissolution. There's a nifty button here that says Run Dissolution. If you click this, it's going to ask you for a method. Just go for the PA method. What it's going to do is it's going to ask you to do a couple things. It wants you to inject this solvent in. I'm going to borrow this. Again, I'm just sort of pantomiming here. It's not a great thing if you're trying to do dissolution without this above. So again, you can open these doors. This is the top valve for the bomb. So you open this, and then you stick this in here as far down as you can, and then you basically inject it in, pull it out, close the valve. That's important. It needs to be pressurized. And then you'll just stay on doors like that. One other thing that I missed, and this is the copy on it, this dissolution stick is typically on the side here. When we're ready for the dissolution, it needs to move over. There's a little spring here, push down. There's also a spring here, push down. And put this thing basically in line here. So now it's basically lined up. It's ready to, you know, down. We're not going to see that in dissolution until we remove our couple. Now we close, and look, this is happy with us. So let's move on. So when you click finish, it'll start the dissolution process. So, you know, again, you should do this when there's liquid in there. But let's click finish. And so what you'll see now is it's heating and pressurizing that top spot. So And it's going to build up until 10 bar Gs. Right now it's 4. It's going up. So we have nothing in there. But you know, as that builds up, once it gets to 10, basically the sample chamber, you can hear it again. The sample chamber comes up, it comes down, and it meets the cup. When that happens, it then opens the valve up there so that the buffer can come down, mixes with the sample in the cup, and then comes out. There's an outer lumen in this thing that leads to this line. This should be in a glass, otherwise it's all over the place. So, and then the sample will come out and refund in what do you call it, the plastic. So, yeah, that's that. Any questions thus far? Makes sense? There's just a few last things that I want to go over. Let's see. Okay, so let's say there was a problem and we needed to remove our sample. We don't have to do this if we've done a dissolution, because at the end of the dissolution, our inhibition tool can come out as well. But let's say I don't think start working. At any time we can click the board and stop the polarization. We'll stop this program here, right here. And then in order to remove the sample, this button which used to say insert sample, now that it knows that there's a cup in there with a sample, now it says remove sample. So what we do then is click this button. It's going to ask us, is the dissolution stick in the operating position? I.e., is it aligned with the VCI? And we already did that, right? That's the operating position. It's straight up and down. It's not off to the side. That's good. And you'll notice too that if the door is open, it won't let you do it. Once the door closes. Yeah. How does it come out? Well, what happens is, imagine this is the dissolution stick of the machine. When the dissolution is initialized, remember this cup is in a sample holder. The sample holder actually pulls it just up out of the liquid feeling. So it's just above the liquid feeling level. That's supposed to be recapitulated on the worksheet if you notice. And then we have to see if there's a liquid feeling level inside the VCI. It pulls it just out of the liquid, but still in the magnetic field. It's important that the dissolution happens still in a fairly strong magnetic field. It's not quite as quick as I think, it's a little lower, but still fairly high. So anyway, it's pulled out, and then the stick goes down, and then it basically catches the cup, and then up comes the stick. I'm sorry, it doesn't come up yet. Once the cup is on the end, that's when it opens the valve and moves the liquid down, mixes up. The dissolution, if you watch, and sorry we're not showing it, but if you watch the dissolution, you'll notice that the liquid comes out, but the stick will still be down inside the machine. After the dissolution is complete, what will happen is the stick comes back up, and so it'll end up in this position, but with the cup on the end of it. So then, afterwards, you'll just, if you move the stick over, you'll notice that the cup is on the end. Is that? You didn't take it off. Right? You pull it off. Yes, yeah. Then you'll pull it off. So usually you keep it on and clean the system, and then you pull it off. So, but yes. So, and
it'll be doing the same thing when you remove the sample, using the stick in there to pull it off.
Exactly. Yeah, thank you very much. Yeah, so actually, you'll see that right now. So this is dissolution minus the liquid. That's all the removing it. So okay, again, we're all set.
Yeah, leave the half door open.
Oh yeah, that's a good idea. So you can see. All right,
if you guys want
so
to come over on the side and see, it's kind of cool.
See the removal. Again, it's essentially going to be the same, more or less the same thing as the dissolution. The only difference from the dissolution stick side is it would stay in the system a little bit longer, so that when the liquid comes, it'll make the liquid go through before it races out. So the next button field here at the sample chamber. There it goes up, it goes down, boom, and it comes up. That's it. And then, if you push this down, there's our cup that we loaded. And it's still full. So, and then you see the system has to put the stick away from the operating position. And then, yeah, this can basically be removed from the stick. For the time being, we're going to keep it on because we need it for cleaning.
I'd say that's not recommended practice to leave. This is the sensor for the door is on the other side, so we can leave it over there for the purpose of demonstration. But when you're running it, you should leave it fully closed. Yeah, it's good practice.
Yeah. So, okay. Very importantly, once we're finished with the polarizer, as soon as possible, and we know that no one else is using it immediately after us, we should click this idle button. You'll hear basically the pump in here over here. I guess it's not. No. Yeah, there. The pump is off now. So I think keeping your ears open can help. And to be honest, if you hear weird noises, you know, if you've been using this and you hear weird noises, I think those are good things to report. Because those can very often indicate, you know, a problem, an imminent problem. So keeping your eyes and ears open is good. Great. Now, the other part of this is cleaning. You know, so we do our dissolution. You're going to see, you know, green fluid left in this line, and it's important to clean this stuff out. Very importantly, you can clean at any time. You do not need this system cooled down. It can be idle, because all it uses is that helium tank and the valves. So that's, you can clean it before you do your dissolution. You should do it after you do your dissolution. It doesn't care too much about the system. We're nearing the end here. So there's some cleaning solution, 0.3 millimolar EDTA used in water. Does anyone know why there's EDTA in this? And also in all the buffers that we use here? Any thoughts? Yes? Does anyone know what EDTA does? Ethylene, thymine, acetic acid. So EDTA, it's a metal chelator. So it basically binds metal ions. Does anyone have a thought why that would be important in the case of hyperpolarized? It's important to note that this bomb and this stick on the inside, it's stainless steel, it's metal. So why would we want to chelate metal ions? Does anyone know of any other chelates that are used in MRI? Have you heard of gadolinium iodide? So it's essentially it's a metal atom that is basically chelated held by a chelator. Gadolinium iodide is a relaxation agent. And the big thing is that iron and metals can act in the same way. So free metals in solution, particularly, I think gadolinium is kind of an exception. Free metals in solution can cause relaxation of our carbons and lead to large losses of zinc. So we always put EDTA in all the buffers so that it'll basically protect the carbons by basically chelating any iron or any metal ions, essentially just keeping them away from the carbons so that we don't lose the hyperpolarized signal. Does that make sense, more or less? So that's important. Also, if you're making your own buffer, that's an important consideration. All right, do you mind if I see here and get this stuff? So when we're cleaning, there are a couple of steps, and then we'll finish. I think we're a little over time, so in order to clean, the first thing we need to do is we need to load this liquid out. We can do it. Open this valve. That's the gears pressure thing. Come out of this gap. To be careful, it can be hot up here. So, same way. So I should mention as well as a safety precaution, when you do a dissolution, please wear safety glasses or goggles. It is possible that something can go wrong and very hot liquid can spew out of the top. You do not want anything like that getting in your eyes. So, all right. Now it's important that we have a cup on the end. Why is that important?
Right.
That's right, yeah. The cup basically closes the fluid circuit. So what we're going to do is this liquid is going to follow the same path as the solution. Out the outer lumen and then out here. So if there's no cup, it's just going to spray out here and then go down that way. So we need a cup. That's also why there's this nifty check box that says sample cup. Like, yes, it's a sample cup. There's one other thing that we need. And that is the place for the liquid to go. So if we did our cleaning, the liquid was in, well, it's not here. So let's not have it going over the ground. That's a good thing. So that's good. Now, so the chase gas, what you'll see when we open this is it pressurizes this system up here, but it doesn't, come out because this is the valve that allows the liquid to come out of the bomb up there. So if we open it, now, so typically our procedure is 2 to 3 mils at the top there, and we do this twice. On the second time, let this run a little bit longer until the line is dry. Just letting it dry out. And once this is working, oh yeah. Absolutely, yes, it certainly can. Just make sure that waste goes into the waste bottle in the hood. Yeah, that's perfectly fine. So, yeah, so did everyone catch that? Just as like a practical point, if you've done your dissolution, it came out into the flask. That flask can be the same flask that collects your cleaning liquid. It is important to do the cleaning as soon after as possible, just for the maintenance of all this stuff. Okay, so this is dry. What I'm going to do is I'm going to first close off the gas. So you'll see the pressure basically drops down, and then I can close the solvent discharge valve. One last step, and then I'll let you go. We also want to dry out this stick. So we usually do this with scrap chin wipe. Fortunately, I didn't get to go over any, alarms or problems with that. We'll have to go over that later. But generally, I think the mode of action is get me. Same thing. Open chase gas, open solvent discharge. See now it's coming out of here. It's not coming out of here because there's no cup. This is the only situation where you like the system. Well, not the only situation. And let that go for 5 seconds. Close. I think it's a matter of courtesy. It's good to let the pressure go all the way down. I know at least when I open that and I hear, and I hear pressure release, it makes me wonder if the user cleaned it. So it's not a big deal. Just make sure that you're diligent with cleaning, and especially note it on. Well, here's some thing with that. I'll let everyone know if there are changes. Okay. All right, and then in order to exit out of here, check, finish. All right. Any last questions on anything on the machine? Polarization.
So I actually want to make sure that the idols that someone else talks to. If there's like a gap in the schedule, like an hour or two, like what's the threshold to say how much an idol can sometimes gap in action?
Good question. I think we've determined that I think if someone will not use it for the next 30 minutes, half hour, then it's good to put the polarizer in the idle state. If it's within 30 minutes, leave it cool down. Just make sure that the person is actually coming to use it.
I don't think there's too much risk to idling it or loss there.
Well, I guess the one thing is that in order to cool it down again, it does require a bit more helium. So, I mean, certainly if the person is there.
But it's requiring helium as it's on too, though. Or
That's true. Though I'm not sure. I mean, this is coming from Mark, at least from what I've been told. You know, if it's, I mean, as it's on idle, the temperatures are changing. This helium is boiling away, so it does take some extra helium to cool them again. So anyway,
all the time it's also on, it's cooling, boiling down helium. If you look at the valve, it's letting more and more helium in, so you don't want to leave the cool down on.
That's right. Yeah.
All right, let's make it cool down.
You mean running one sample and then loading another one? Yes. Well, you certainly should begin as soon as